so in this video we're going to talk about similar matrices. Okay, so what does it mean for a matrix to be similar to another matrix? Okay, all right. So what this means here is, so let's define similarity, right? So we define SIM, right, similar matrices. Okay, so we say that square matrices A and B are similar again, size n, right? So n, so we'll just say n by n, but just square in general, right? Are similar if there exists a non-singular matrix S such that A equals to S inverse BS. Okay. All right. So that's what it means to be similar, right? Not equal, right? We know what equality is. We defined it here in that sense when two matrices are equal, when we have entry by entry. But here it says that they're equal with the help of this matrix S. Right. So, for example, let's take a look at, let's say that we know we have a matrix B, right, defined by -13, -8, -4, 12, 7, 4, 24, 16, 7. Right? And let's say we have S to be equal to matrix 1, 1, 2, so another 3 by 3 matrix, -2, -1, -3, and 1, -2, 0. Okay, let's say we have these two matrices, and from there we find S inverse. So we find S inverse, and this turns out to be -6, -4, -1, -3, -1. 5, 3, 1. Okay. All right. So here, let's say we perform the operation S inverse BS, and that turns out to be this matrix -1, 0, 0, 0, 3, 0, 0, 0, -1. All right, that is our matrix A. Okay, now we get this. Now this doesn't always happen, right? S was chosen in such a way that we made this happen, right? We forced this to happen where we had this diagonal matrix. Now, I say forced because let's think of if I wanted to find the eigenvalues of a matrix, right? Looking at A, looking at matrix B, we can say, all right, well, sure, I can do it, but it will probably be tedious. But now let's take a look at matrix A here, right? And our task to find the eigenvalues. This actually now becomes a much more easier operation, right? I can actually just look at it and determine what those eigenvalues are, right? Because then here, this matrix just becomes, right, -1 minus lambda, 0, 0, 0, 3 minus lambda, -1 minus lambda, right? And here I will do the cofactor expansion, right, across really any row, any column, right? Because whichever one you choose, you're going to get 2 zeros in there, right? And you see right away, right, this determinant here is really just taking the determinant by multiplying all the products down the diagonal. And you get doing that, setting up your characteristic polynomial in that way, right away, you get the roots, right? It's already factored, right? There's no additional work to do that, right? So we can see why it's beneficial here. Now, the question is, can I bypass finding the eigenvalues of a matrix B and actually just do the eigenvalues from a matrix A? Well, it turns out that yes, but why can we do that? Why is that possible? Right, so it turns out that similarity is what's known as an equivalence relation. Is an equivalence relation. So what that means is that it is reflexive, excuse me, right? All right, so that means that A is equal, it's similar to itself, right? So in other words, the three properties are reflexive. A is similar to A. All right, and yeah, here we could say the identity matrix is that matrix S that you can generate to show similarity. All right. It is symmetric. So what this means is that A is similar to B, then B is similar to A. Okay, and we could see that because if A is similar to B, then we have this relationship here. All right, but again, S is a non-singular matrix, so through left and right multiplication, we could write this as S A S inverse equal to B. So B is similar to A, and A is similar to B. And it also has the transitive property. So that means A is similar to B. And B is similar to C. Then A is similar to C. All right, so that's what makes it an equivalence relation. But more importantly, in addition to that, what we can do is they are the same class, so they share important properties. And one of those important properties comes from this next theorem, SMEE, which states that similar matrices have equal eigenvalues. Okay, so if A and B are similar, then their characteristic polynomials are similar. In particular, they have the same eigenvalues with the same algebraic multiplicities, right? And that's where it's helpful to know that, or to have that property be a consequence of similarity, because now I can work with the much more easier to work with diagonal matrix, right? So here, why is this true? So let's say in our proof here, okay, so let's recall that A and B are similar. So just keep that in mind, right? As our hypothesis, we assume this to be true. So the characteristic polynomial of matrix A is the determinant of A minus X I N. Okay. And here we have, okay, so now that means that I can, because of its similarity, the hypothesis, this is equal to the determinant of S inverse B S minus XI. Okay. All right, and then here we can rewrite this as here S inverse B minus X IN S. Okay. All right. Okay, and then from here, using the properties of determinants, we have determinants of S inverse, determinant of B minus X IN. All right, and then determinant of S. Okay, and then from here, right, what we see is that these simplify to 1, and we're left with the determinant of B minus X IN. Right, which is a characteristic polynomial of B of X. All right. Okay, so here, a couple things. I did realize that I just skipped a step here in coming up with this property here, right? Just keep in mind here what we can, since S is non-singular, we can write I as S inverse times S. And hence you can factor it. Well, if you plug that in there for IN, then you can factor it in this form here. Okay. All right. Okay. All right, and they have the same characteristic polynomial. Now, this is note that the converse is false. If they have equal characteristic polynomials, they do not need to be similar, right? But what we want to get from here, the important part here is that similar matrices, they share eigenvalues. And the most desired outcome is when a matrix is similar to a diagonal matrix, right? Because now we can see now calculating the eigenvalues is a pretty trivial problem in that case.